Hello, this is Kerry Schutz with MathWorks, and this is our sixth video in our series on modeling PLLs using mixed signal Blockset. In this particular installment, we are going to take a deeper dive from where we left off in video 5, and we're going to take a closer look at how the phase noise was generated under the Ring Oscillator VCO block, and how we measured the phase noise, the impact of said VCO phase noise, under the phase noise measurement block. So we're going to be taking deeper dives in this video. So this video is not just about the implementation details under these blocks and when it comes to phase noise, but you're also going to see a lot of the very, detailed under the hood details of how you would navigate in Simulink and how you would modify the behavior of a block. So this would apply to anything you do in Simulink where you want to go in and go under the hood and see how things are behaving and possibly modify the behavior of the block. So that's what we're going to be doing a lot of here today. In particular, we're going to be doing the same thing we did before. We could break links on blocks, which we've already did. You can see the arrow in the lower left-hand corner where we've broken the link to the library so we can easily navigate and modify the block. But then going further, we're going to show how to look at what are called callbacks associated with the blocks. And that basically means for many blocks in Simulink, you can optionally put a mask on the block, which is what we've done here. That's why you see when you double click on the block, you see a mask. You don't see the implementation details. Just when you do the double click, you would only see the details if you click on the arrow in the lower left-hand corner as far as the block level details. But this mask typically, not always, has MATLAB code associated with it. We call it the mask code or initialization code. And we're going to go underneath the block and show how you would see that code and modify it. Further, for these blocks, you can optionally add things like open function callbacks and stop function callbacks. And that basically means every time you open the block or every time you the model runs and stops or pauses, you can assign a MATLAB callback action that executes every time said action occurs. So we're going to be looking at all of that and more in this video on our under the phase noise hood video. And again, I want to emphasize that although I'm focusing on the Ring Oscillator VCO noise, as I mentioned in the previous video, in reality, you would have many sources of phase noise contributing to the overall phase noise of the PLL. Again, on the reference, charge pump, loop filter, the divider, again, the VCO. You could have phase noise pretty much introduced everywhere, and there would be that two categories of types of noise that would lead to the overall phase noise. You would have the jitter or timing type noise or phase noise on things like the reference, the phase frequency detector, the ring oscillator, and the divider. And then you would have amplitude, noise, voltage, current noise introduced in things like the charge pump and the loop filter that would also manifest its phase noise in the output. And on the loop filter in particular, it's not too hard to add the effect of thermal noise, and again, which would lead to phase noise. There is an impairments tab on the loop filter. You could enable that, and then you could generate thermal noise based on a particular temperature that you specify here. And that, of course, would apply to the resistors in your loop filter. Okay, so we have to start somewhere. So let's just initially dive in on phase noise generation. Again, there's going to be two parts: phase noise generation here, phase noise measurement here. So let's start we'll just drill under the ring oscillator VCO block. If you recall, it's a single stage behavioral ring oscillator structure, delay operator in a feedback loop with an inverter, where we feed it with an ideal half period delay controlled by a voltage, and then we perturb that by some amount of jitter, which is filtered or colored by this flicker filter block. And the coefficients or the design of that flicker filter block is handled by code underneath this block in its mask. So in terms of setting up the coefficients for this block, and in terms of setting the level or the variance of the period jitter noise, that's all controlled by some MATLAB code. So this is really where the magic of this block occurs for phase noise. So let's go ahead and take a look at Well, how would you look at how that was all handled? Because if you look right now, that all these parameters are hard coded. Of course, there was no human that typed that in. That was actually MATLAB and functions calling, which actually entered these parameters into the block. No humans involved. Okay, so let's go up and let's right click on the block, Ring Oscillator VCO. Let's go to Mask, Edit Mask. Okay, that's going to bring up our mask editor for the block. This is where you can create the mask and modify the mask and add MATLAB code. And the typical control you would add on a mask would be things like edit boxes and check boxes, but there's all sorts of other controls you can add as well. And then there's this all-important section where you can add code. I am going to click on it. And if we go to the top, you see there's things like initialization code and other functions, extra buffer callback, in buffer callback, add phase noise callback, estimate parameters, and so on. And all of these are actions associated with buttons in the mask. Now, I am in particular, I am going to look at how the block is initialized under the mxblocks.vco.configure ring oscillator function. So I'm just going to copy. I could say open it. I could say copy it. Whatever. We can just do open, and that brings up our editor, and we can see that this opens up a function. This is in the shipping files with MathWorks, MATLAB, 22B, Toolbox, MS Blocks, etc., down to configure ring oscillator. And if you look at this function, it's to configure the ring oscillator VCO model at the beginning of the simulation run. And so there's some immediate references to period, jitter, and flicker filter. Okay, and that's what we're focusing on here now. So the first thing the block does is it gets certain parameters from the block. It communicates with the block. It says, give me the output frequency or the free running frequency of the block, like F0. Okay, and it assigns that to F0. And it gets the phase noise offset frequency, assigns them to F, and it gets the period jitter specification, the corner frequency specification, and it assigns those to local variables under this function. It gets the amplitude of the VCO output. Okay, and then it does some conversions, based on the free running frequency of the VCO, the maximum phase noise offset number. And ultimately, what it's doing is it's going to scale the specified period jitter number to a particular sigma value. And that sigma value is squared, and that becomes our variance on the block, which I was just showing you under the hood, this block right here. That becomes the variance number you see specified here. And that is sigma gen squared here. Okay, so that goes into that block. And there's also a sample time. And the sample time, of course, here for this block, it is a discrete time implementation. It's based on some oversampled value of the maximum phase noise offset, because all of this action, all of this phase noise generation action is not taking place at the free running frequency of the VCO. It's taking place at the bandwidth of the phase noise generation. So if we had for instance, a 10 megahertz offset in our phase noise, maximum phase noise, then we would be oversampling that number by some scalar value, let's say 10 or 20. We wouldn't be basing the phase noise generation based on 2 gigahertz. So that, again, it's more efficient, only to focus on, rather than oversampling based on this, we're going to oversample based on the maximum phase noise offset. Okay, so and then the interesting part of this function occurs under step 2, where we calculate the poles and zeros for the flicker filter. The flicker filter is a second order section filter. It is a fourth order pole zero filter built out of 2 second order section filters and cascaded. And what we do is we take the flicker exponent, which in our case I believe was just 1. It was 1 over F noise before the corner frequency. And we create an exponential index, and that ultimately maps to a pole zero factor. That pole zero factor you can think of as a scaling factor that describes how far the poles and zeros are spread apart. That's why it's called a pole zero factor. And as you can see here, the larger that exponential index, the more spreading there is. And so here we go. The poles are spaced logarithmically. You take the corner frequency times 2 pi, it's all in radians here, and you take here, I guess you could call it 3 orders of magnitude. You've got 4 specific values specified, and you're scaling the corner frequency by those logarithmic values, logarithmically spaced values. And so you got your pole locations. Then you've got your zero locations, which are scaled by that pole zero factor. Now, of course, they're interleaved. They're between, for instance, minus 0.001 and minus 0.01. And then there's one between minus 0.01 and minus 0.1. But where exactly it's placed, again, is based on that 1 over f scaling factor, or pole zero factor. And so in our case, I think it's 10 based on what I had. So the poles would be, the zeros would be located at the poles times the square root of 10, or approximately the poles times 3.1 or so. Finally, now you've got your pole zeros, and that's, again, it's a 4th order pole zero filter. Now the next step is some implementation details of how you want to implement that pole zero filter. In our case, it's a 2nd order system matrix. And so we take those pole zeros and we put them into a 2nd order system format with the, the A's and the B's and the numerator and denominator. And then finally, we create or reset the coefficients under the block. So we do a set param, the filter with the biquad coefficients with that 2nd order system matrix and the amplitude values. Okay, so now we're good. We've described how the flicker filter was designed or implemented. Now we go to how the phase noise is measured. The phase noise is measured, again, under our phase noise measurement block. And just like the Ring Oscillator VCO block, we can also dive under the phase noise measurement block. And I believe I went over this briefly in video 5, where I said, okay, well, we're going to measure phase noise. We have to make sure to avoid measuring phase noise in the transient region of the PLL while it's trying to lock. So that's what the hold off time here is specified, or what it's used for. Again, don't measure phase noise in the midst of a locking operation of the PLL. Once we are locked, the hold off time, the hold off time in this case goes from, I should say the block that's going to measure phase noise gets enabled. And so we just go high after so many microseconds. If we dive under this block, where if you notice, the block itself is not directly doing the phase noise measurement. All it's doing is logging zero crossing time. So we've got the PLL output here on input 1 called sig. We are looking for positive and negative going transitions on the PLL output. And when we get those, we store the data to a temp file. We store the zero crossing times to a temporary file. In this case, it is a mat file. If I were to make this big enough and stretch it out long enough, we're going to see that we're saving those zero crossing times to this particular file, this user case shoots app data local temp zero crossing mat file. And at that point, we're really in a mode where we could wait till the simulation ends, and we're going to grab that zero crossing data, post-process it, and then compute a phase noise spectrum. Or this block even allows you to compute that phase noise spectrum before the simulation stops while it's running, using some intermediate zero crossing data. Okay, but for now, let's assume we have logged a bunch of zero crossing data. It's all in this file. And now we want to post-process it, or again, post-process it while it's running and display the phase noise spectrum. How would you do that? Well, again, we have to dive under the block and see where that code is and open it up and look at it and or modify it. So let's do that. Let's go right-click on the block. This time, instead of going to mask and edit mask, we're not going to look at the mask code. We're going to look at code under the block properties, in particular callbacks. So we go to the callbacks tab, and there's all different types of times where you could assign MATLAB action to this block. Anytime a close operation is initiated, anytime you initialize the block, anytime you have the models loaded, anytime you move the block, anytime you open the block, anytime you hit a pause in the model, or anytime you hit stop or start. So under this block there, if you notice the asterisk, there is an action associated with the pause function called phase noise stop function, and also the same action associated with the stop function, phase noise stop function. I am going to open that up and look at how that's implemented. Okay, I'm going to just copy that. All right, cancel. We'll go over here, go to the MATLAB prompt. Go here. Let's say edit that function. And here is our phase noise stop function. Now, from our phase noise stop function, we do have, let's see, we can go down here and look at this. Yeah, we've got a little navigation to go. The first thing I'm going to do is just kind of skip some of the details, but one of the things the block does is you notice it immediately grabs that temporary file, that mat file where we logged all the zero crossing data to. Okay, and that data ultimately gets passed to another function. There's a few intermediate functions get used here. That data is converted or assigned to T clock, basically the zero crossing times. That T clock data is passed to this MS blocks VCO phase noise wrapper function. There's T clock right there. Let's open that up. That in turn, there's a little bit more logistics, hoops to jump through, that ultimately calls MS blocks utilities phase noise a time domain. So we can open that up. And again, if you look at all these functions, you can see the path of where they start. These are shipping MATLAB files, which again, we don't recommend that you modify these, but these are good for understanding. And if you were to modify them, which of course you can, you would always want to keep a backup of the originals just to be safe so you could get back where you started. In any case, here's where the real work is done when it comes to computing phase noise. You notice the zero crossing data here is passed in, no longer called T clock, it's called zero crossing data. Same thing though, resolution bandwidth, frequency offsets of interest, okay, are passed in. And these are, again, the phase noise offsets. So again, if we scroll down from the top of the phase noise measurement function, the one that does the real work, we're going to see where it picks up the zero crossing data, takes a diff of it to come up with a series of DTs, our differential times. And then ultimately what we do is you take a mean of those differential times to compute some overall average half clock period. Again, for our case, since we had a 2.1 gigahertz clock, the average TS would be 1 over 2 times 2.1 E9. So approximately 1 over 4.2 E9 in our case would be our average TS, a very, very small number. So I'll just do that over here at MATLAB to give you a feel for what that is in our case. That would be approximately 238 picoseconds. Okay, approximately but again, it's going to be whatever it is based on the PLL configuration that you have. Okay, so we have that now kind of average or mean TS number, which of course you can convert also to a mean frequency for the PLL lock. And then finally, we get down here to this really interesting line where we're computing something called sign phase error, or really a better name for it would probably just be phase error. The sign part is not so relevant. Here, what we're doing is, but I'll put it back in since, well, I guess down here I'm using sign phase error, so I don't want to change it in the middle. So in any case, what we're doing is we're taking the zero crossing data. We subtract off the first point because we really don't care so much about the absolute time of the zero crossings. What we really care about is the relative zero crossings time from time zero. So this just forces us to start from time zero in our zero crossing data set or vector. Then what we do is we subtract off the kind of ideal sample times from it. So therefore, we're computing kind of a jitter from this. We're computing kind of offsets from the ideal sample time to the actual sample time. And that's what comes out of this expression, all scaled by pi over TS. Then what we do is, because that's rather coarsely sampled data, we perform some interpolation on it. Remember, we only have zero crossing data at the actual zero crossings. That would be 2 times per cycle, one for the positive edge, one for the negative going edge. So what we do is to get a little finer estimate, we're interpolating that in this section of code here, and we're interpolating that based on a delta T which is computed as a function of the maximum frequency offset. If you recall, our maximum frequency offset was 10 megahertz. And in this case, using a spline interpolation scheme. From that point, now we get into the spectral processing. So now we have something called sine phase error discrete. And again, the sign's kind of misleading. We could probably just call it phase error discrete, phase error oversampled. And from here now, we are going to get into the spectrum computation. It's an FFT-based computation where we take the interpolated phase error vector, and we compute, we create a spectrum analyzer object. This is all using a DSP spectrum estimator object as part of DSP system Blockset, where we specify the method of spectrum computation, in this case Welch. It's going to be one-sided in terms of dBW. And, again, it's an FFT-based approach. It's going to be a power spectrum density computation, not a power spectrum, because phase noise is a power spectral density type of spectrum. And that's relative to the carrier. And then finally, we get down in here and we go through the data in blocks, in FFT size blocks, and we compute an FFT one block at a time, and then we average it. Okay, so we perform a spectral average. In this case, I don't know how many averages, whatever the number of averages we specified. Remember, back in the user interface, in this case, I had 4 specified. So in this case, when I'm going through the loop, there's going to be 4 times through this loop to compute 4 spectral averages. And that is finally what gets displayed in the plot that you saw at the very end of the simulation. So again, going back and reviewing, if I go back to here and plot phase noise, this is the result of all that work that we just performed. We had 4 averages, center frequency 2.1 gigahertz, phase noise plot, again with offsets from 10 kilohertz all the way out to 10 megahertz. Okay, so I hope that's been helpful. I know it's been tedious, I know it's been long, but I wanted to kind of be thorough about it, not skip the details, to let you know about how we compute phase noise, how we generate phase noise, and how you can learn how to look under blocks at the underlying code, if not just for learning or for possible modification yourself, or when you create your own blocks in the future. All right, thank you. Till next time.